Log on, tune in, find out. Another good idea from Cambridge.
From Weizmann Institute, and he'll talk about Vertex sparsifiers.
All right, thank you very much. It's a pleasure to be here. Okay, so I'll tell you about Vertex sparsifiers. You see soon the definition. And this is joint work with Matthias Englert, Anupam Gupta, Harald Rake, Inbal Talgam Cohen, and Kunal Talwar. Okay, so as a motivating example, let's think about this problem called the graph bisection or minimum bisection. So the input is a graph, G, and you want to partition the vertices of the graph into two sets of equal size. It's very important they're of equal size. V1 equals V2, the size of equal V1, V2. And the goal is to minimize the number of edges crossing between these two sets, the cut size. Okay, so here's an example. Maybe this is you cut 4 vertices in each side, and it's of minimum, we call it cost. It could be that the edges have costs or capacities, although we can think here about the unweighted case as well. This is a very well-known problem, well studied. It's known to be NP-hard and so on. I won't get into these things. The best algorithm that is known, so given the input graph G to find the minimum, the best cut in this, according to this objective, the best approximation algorithms we know, which means that the algorithm that runs in polynomial time achieves approximation order log n. Okay, this is due to Rake. And it is well known to be a central problem, so I'll use it as an example. So here is a version of the problem, which actually I'm going to call it terminal bisection because we're going to deal throughout the talk with terminals, which is just a subset of the vertices. Actually, I think in all these papers, including my paper and previous papers, it's usually called kind of like a Steiner bisection. Okay, so I don't know which one is better. I think it's better to think about it this way. Okay, so what is the setting? You have similarly a graph G, but now you have also a set of terminals, just a subset of the vertices. And the goal is to find again a cut of the graph, but now instead of splitting equally all the vertices, what I care about is that the terminals, the set K, is split into two equal size sets by the cut. Okay, so V1 intersection K has to be equal to V2 intersection K. And again, you want to minimize, this is a constraint, and you want to minimize the number of edges crossing the cut. Okay, so all of a sudden, the same graph, if the big yellow circles represent terminals, then now the best cut, the optimal solution is different because the cut we had before did not split the terminals into equal size sets. Okay, so this is the version of the problem, terminal bisection. Okay, you can think of this like as a cousin of the previous problem. And it turns out that if you use the same algorithm that is known by Rake, then you get the same order log n approximation still applies. But one may ask, maybe if K is very small, so I'm going to use throughout the following notations. Little k is just the size of the set K, right? So little k is the number of terminals. I didn't say it before, but n is the number of vertices, right? So instead of doing something like log n, maybe we can do something that depends on k. Hopefully something like log k. That'd be really nice. But can we do any function of k? So depending only on the number of terminals. And similarly, so this is just an example using the bisection problem, but you can ask similar problems, similar versions of other problems like linear arrangement, routing problems, and so on. I won't get into it. This is just a motivating example. Here is another, so that's one problem we want to solve. Here, think about it now as a tool, Vertex sparsifiers, okay? And this is going to, the definition I'm going to be using is with respect to cuts. If you know the subject, then you know there's also something similar with respect to flows. And if you don't know, so just easier for me to define it this way. If you know the difference, then throughout this talk, I'm just going to use interchangeably the two, even though they're not really the same. Okay, so we see again we have a graph G and a set of terminals K. But what we want to do now is find a new graph H, just on the terminals, just on K. So instead of a graph of size n, the big graph, we want a small graph of size k, just on the terminals, the vertices that we were told they are the most important ones. And the idea is that this new graph will have the following property, that for every partition of the terminals k into, say, s and t, the minimum cut in the graph G, the minimum cut that separates these two sets, is the same as the minimum cut separating the two sets in H. Okay? So what does it really mean? So here is by picture. So we have the yellow ones are the terminals, and maybe these are the edge costs. Now here I'm going to use edge costs or capacities, and I want the graph just on the yellow vertices. This is of course a very simple example. You can just see which edge is the most expensive one, and that's of course going to determine all the cuts, the relevant cuts. So here these are the ones in the red circle, and then we can create from this G a new graph, which is just a triangle with this edge cost, the one in the circles, and it's easy to see that any. So if you want to split, say, the top terminal from the other two, in this graph, the minimum there's basically just one cut. It's this one, of course, 12. If you want to do the same thing, sorry, I should have taken the minimum one, but if I want to do it on that graph, I can do similarly, look for the cuts that separate the top terminal from the two at the bottom. Okay, so I mixed the numbers. I should have taken the minimum number on each path. So instead of 9, it should have been 1 and so on. Okay, but the idea is that if we care about any partition of the terminals into two sets, S and T, the best way to partition them to find a cut in the graph that separates these terminals exactly into this S and T, I can actually read it from this graph. Okay, by looking the same partition here or looking the min cut here. Here it's very simple because if I know, it's a partition of all the vertices, so it's one cut, it's defined. Over there, I have to do kind of like a min cut computation, where I force the subset S and the subset T to be on different sides. It's like what's known single ST cut, what's called ST cut, usually with little s and little t.
So normally we think also of k as reasonably big.
Yeah, so think of, let's say k is like log n. So why am I saying log n? So it's bigger than constant, but somehow log k is much better than log n. Right? If it was just root n, then maybe the difference is not worth the effort.
Yeah, if it's like log n and still for a longer time you can go over all possibilities. So for example, for bisection, you still
Right,
k,
right, okay, good point, yeah.
So
So maybe log squared, yeah.
Log squared.
Yeah. But also, I mean, yeah, for the example, okay, we'll get to it in a minute. It's not only about computation time, it's like a small representation of the same thing. So you can think of it as like storage or space. Which is the next point. It's kind of like, we kind of like take this big graph on n vertices, we compress it, in quotes, into a graph of size k, on much fewer vertices, because we only care about the terminals, then intuitively, it might be okay, it might be possible to actually represent using a graph of size k. So information theoretically, it's kind of like we have 2 to the k possible cuts, right? All the partitions of the set k into this S and T. So, maybe it's okay using one graph of size k, we're going to have something like 2 to the k values. And maybe it's possible to compress all these 2 to the k values into one graph of size k, which means like k or k squared edges, right? So it's like a much shorter, a succinct representation of all the cuts. This is just compressing the information. And in terms of computation, if we had to do some computation on the big graph, we might compute it here, and that might be a smaller graph, it's going to be faster and so on. Maybe we do it only one time in the beginning, and then we have many problems to solve on the same set of terminals. Then we're going to have to solve each one of them much quicker because it's a small graph and so on. Obviously, there's like an approximate there, so we might not be able to maintain all these values exactly. In particular, this would be, if we do this reduction or transformation, then we could solve the minimum bisection on this graph, right? Because we're going to, whatever we do, like a standard bisection in this graph corresponds to the terminal bisection on the original graph, right? So that's the connection to the example I gave in the beginning. If we find here the best partition into 2 equal size sets, of course it's not possible because it's an even number of terminals. Usually it's assumed to be odd, or sorry, it's an odd number. It's usually assumed to be even. But in principle, that would be a way to solve the problem by transforming the graph G into this graph H. And as I said, there's a version with multi-commodity flow. If you know about it, then you know what I'm talking about. If not, then it doesn't matter. It's just easier to think of it this way. So what's known about this object? So this object that we just saw, I'm going to call it a vertex sparsifier. Right? We sparsify the graph by removing vertices, or keeping only few vertices in a way. It was suggested by Moitra, and then the construction was improved by Layton, the paper by Layton and Moitra. Basically, it's known that there's like sparsifiers with quality, which is log k over log k, order of log k over log k. So what is quality? In the approximate value here, this is up to multiplicative. Everything is preserved up to multiplicative factor. That's the quality. So I didn't bother defining it exactly because we don't really need the definition this way. So it's possible to build such a smaller graph H with quality log over log k. If you want to do find one efficiently, which means in polynomial time, then the bound is a bit worse off. Is worse off by a log k factor. And if you think about it this way, then you can actually get an approximation for this terminal bisection problem with factor log cubed k, roughly. Why? Because you do this step in polynomial time, and then you apply the algorithm that you know on this smaller graph of size k, so that's another log factor approximation, and you can translate the values back, and then that's why you get this roughly log cubed k. And similar, you get polylog of k approximation for other problems instead of whatever is known in terms of n. Right? Because now everything depends. The point here is that it depends only on k, independent of n. One issue with this result is that, so that's one issue with the result is that H is not very simple, even if G is. What does it mean simple? Well, there may be more than one definition, probably, but think of like just if G is planar, you'd like H to be planar as well. And similarly, whatever property you know about G. Maybe if G is sparse, you want H to be sparse. Maybe some other, so different versions. So here is what we show in this paper. We can actually do the polynomial time construction, achieve the same bound as the existential bound that was known for before. So before there was like a gap between the first bullet and the second bullet. So I actually can do find efficiently also the this log k over log k quality. We can also find something which I'll tell you later. It's like a tree-based sparsifier. So it's a sparsifier that has some structure of a tree, and I'll tell you about it. And it's a bit worse off. It's only log k, but once it's based on the tree, many problems are very simple on trees. So it gives a good structure for algorithms. In particular, if you do this tree-based sparsifier, you get order log k approximation for terminal bisection, right? Because basically it's like solving this problem of minimum bisection or graph bisection on a tree. When the graph is a tree, and on a tree you can actually solve it exactly. So and you paid log k in the transformation. And similar improvements for other problems. Really, what tree-based over there means, it just means it's a convex combination or a distribution over trees. So you don't get one tree. So whenever you see the word based there, like tree-based, it's going to mean a distribution over trees. And for this problem, it doesn't matter. It's a distribution. You just take a few samples and take the best solution among these few samples. So in our context, it's the same as just one tree for bisection. Now, I should note that similar results to the ones above here were proved independently also by Makarychev and by a different paper by Charikar, Layton, Lee, and Moitra. So, although somewhat different proof. I think ours is simpler, but... and then another result is about the issue that I said about like planar. If G is planar, can you get H to be planar? So what we can show is that if G is planar, then we can get a sparsifier with quality constant. Okay, this is actually was known from before. Okay, the existence of this was known from before. The algorithm was a bit worse, but we also get that H is planar based. So what does it mean planar based? It's a distribution over planar graphs. Okay, so you don't get like one planar graph that is approximates G very well. We get a distribution over planar graphs, and I will see the definition later again. So in fact, this construction is that the way we get H to be planar is we just use only minors of G. So obviously, if G is planar, then H is planar, and therefore the same construction actually holds for every minor closed family. It's just easy to talk about planar; it's very concrete. So this is kind of like a list of results that we have and can be derived for different problems. I think I already told you the important ones, which is like the three at the top. And these are kind of like problems where you can apply this. And you can see like previously we get something like dependent on n, we get something say log k, previously was log squared k, and so on. So this is kind of the flavor of the improvements you can get from these constructions. But here it's like Steiner bisection or terminal bisection, right? It's like the last one is okay. Okay, so how do we get this? So we'll have to talk about this connection between, now I'm going to call it flow or cuts, and the duality between flow and distance. So there's a beautiful connection between this notion of a sparsifier, which is what we discussed, right? You want to be faithful representation of flows or cuts. From duality perspectives, by using duality, somehow we look we end up looking at embeddings, which maybe everybody here understands maybe better. So where the goal is to faithfully represent distances, right? So somehow we go from one to the other, and I think this connection goes farther beyond the context we're talking about. I'll be talking about today, but let's focus on this one. So there's this beautiful theorem, which I'm going to call the transfer theorem, proved by initially by Recke, and then somehow refined, and the statement and the general version was crystallized by Andersen and Feige. So here is the theorem. I haven't defined everything, so we'll do that later just to get a sense of the duality between these two objects. So suppose we fix a graph G and a collection, this calligraphic M, of mappings between edges and edges. There's something wrong there. Okay, some sort of mappings between edges in the graph. I'll give you the details in the next slide. Then there's like a if and only if statement that holds for every factor row. The first one assertion says that for all edge lengths, right, every edge length that you put, there is a probabilistic mapping with stretch row. So stretch is just distortion. So this is kind of like there is an embedding with distortion row, no matter for every. It has to be something. This mapping is like embedding into trees or embedding into Euclidean space or some sort of like a family, a fixed family of mappings. So there's an if and only if. The second assertion says that for every edge capacities that are you can possibly put on the graph, there is a probabilistic mapping with quality, and quality means the congestion in the sense of flows, but in the sense of cuts that we discussed before, it's just quality row. So it's the same row appearing in both. Okay, so we'll talk about it in the next slide to kind of like unravel the definitions. But basically the point is that it's the same row. So if you know there are good embeddings, then you know there are good sparsifiers, and vice versa, but at least the way we're going to use it, it's in the way that we know there are good embeddings from previous results or something, and therefore we're going to deduce that there are good sparsifiers by this transfer theorem. And this is existential argument. You can actually get an algorithm for this, but let's not worry about it. So just one thing about this probabilistic mapping. So whenever you see this probabilistic here in these slides, it's just going to mean a convex combination of mappings. So if these mappings correspond to all possible trees, then a probabilistic mapping means just a convex combination of trees or distribution over trees. Okay, somehow it appears over and over again, sort of kind of like a zero-sum game principle. So you can only say something about like a convex combination of objects in this context. Okay, so I have to tell you what are these edge mappings, and then hopefully read the theorem again. So what are these edge mappings? So remember we fix a graph G, and we let P of E just be all the multisets of edges. Okay, it seems like a weird definition. Think of it just like, it doesn't really matter, but it's convenient to think of just all possible paths. Simple, not necessarily simple, sorry, paths in the graph. And so a path is just a collection of edges. It's a multiset because if it's not simple, maybe use the same edge again. Okay? So a mapping M is just you map every edge to a collection of edges. Okay, we'll see soon how to use it, but just know that if you have this mapping, like a function M from the edges to paths, then you can also think of it as a matrix whose coordinates are, matrix of size E by E, where the entry M, E, comma, F is just the number of occurrences of F in the image of M of E. Okay, so if M of E is just like a path, then you think like as a row in the matrix with a lot of zeros and ones whenever you use the edge. Or maybe more than one if there's multiple times. So let's do an example. Hopefully it will illustrate the main idea. So let's suppose this is the graph G, on n vertices we have 1, 2, 3, and so on. And we fix an embedding of G into a dominating tree. So I hope embeddings I don't have to define. So here is a tree T. Maybe there's like a mapping from G to T, and let's say this tree, well, I didn't put edge lengths, but let's say it's dominating tree.
What is dominating? Staying?
No, dominating means that the distances in the tree are greater or equal distances in the graph. And for now, if you notice, I ignore the terminals. Just on the entire graph, there are no terminals, because I'm basically doing the simpler version from Reke's proof. Yeah, so just this is our bigger, that means dominating. But let's suppose we fixed an embedding of G into this tree, and for concreteness I chose like a star-like tree. Okay, we want to do this in a star-like tree. And what we could map every edge UV in the graph to kind of like, think of like the shortest UV path in G. So okay, maybe don't look at the things here, look at the picture. So what is S1n? Is like, it's supposed to be the shortest path between the vertices 1 and n in the graph. Let's say it's like these two blue edges. Okay, and maybe the shortest path between vertices 1 and 3 is this S13. Okay, and let's suppose we fix these shortest paths. We know maybe if there are ties, we break ties or something. There are these shortest paths between every pair of vertices. Now what we want to do is do this routing according to the tree structure. So let's suppose we want to route, because we fixed this tree structure. Suppose we want to route this, sorry, so what I mean by this path, S1n, this path corresponds to this edge 1n here. Okay, and this path from 1 to 3, the shortest path corresponds to the edge from 1 to 3 over here. Okay, so this is basically some sort of mapping. And now if you want to route, say, the edge 2, 3, from vertex 2 to vertex 3, this edge E, then because we're using like this tree routing, we have to go along what the tree says. And the tree here is very simple. How do you go from 2 to 3? You have to go through the center of the star. You have to go from 2 to 1 and then go to 3. Okay? And what would that be if you look at G? Well, the edge 2, 1 here corresponds to the edge 2, 1 there. The edge 3, 1 here corresponds to this path over there. And we get this path. Okay? So in some cases, the edge E is mapped to itself, like this edge 1, 2. But in some cases, like this edge 2, 3, it is mapped to a route which goes like all around. Okay? Because we have to route according to this tree. Okay, so basically every edge here, like 1, 2, is mapped to this shortest path in the graph. And if we want to go from 2 to 3, we have to follow one shortest path and another shortest path. But even if 2 and 3 are connected here by a direct edge, we're not going to take that direct edge. We have to route according to this tree structure, even if it takes us very far away in the graph, like here, all around. Okay, so this way we have some kind of like, for every edge, we have a path, which is like, how do we actually go from vertex 2 to 3, and not necessarily through this edge. This is just the mapping. And now you see why, if there's like a tree structure, it's very difficult to work with a tree structure. I mean, it's going to be in general much more expensive to go through tree, using like this tree structure or tree routes. So now, to really understand what the transfer theorem says, you have to look at the following concept. So you take this mappings M. So maybe you take this family M to be all possible trees like this. Okay, it's a very large family, but we don't care. Just define it to be all possible trees. Okay, so what are the distance mappings? So there's like this duality between distance mappings and capacities, or flow. So distance mapping, if we're given also, so far we have fixed the graph G. If we're given also a length, edge length L, then you can see what are these paths doing to every edge. So what is the stretch of an edge? Well, you have to see what happens if you go along all these edges. So this is just summation over all the edges that are used in the path. You take the length of each edge and you compare it to the length of the original edge, right? Like the length of the route all around compared to the length of the edge. That's the definition. Now we're going to take, instead of one tree, we're going to take a probabilistic version. So you're taking expectation over a distribution. Sorry, this D, calligraphic D is supposed to be calligraphic M. Sorry, that's my bad. I tried to make the notation simpler. So basically you take the expectation of a family of trees. Okay, and then you look for the worst edge. Okay, so hopefully if you take a family of trees, then for every edge, the expected stretch is going to be small. Okay, I mean, I wrote the exact definition, but I hope you've seen something like this before, so you have a good feel of what it means. Right? If it's like embedding into trees, this is just the length of the route in the tree divided by the length of the original edge, so that's the stretch. Because dominating is always bigger than 1. Then you take a distribution over trees, so you take the expectation over all trees, and then you see which edge was stretched the most in this sense, in this expected sense. And then there's the dual notion of capacity mappings, so which is if you give every edge a capacity, how much flow you can route, basically, then you define what is the load of the edge. Well, it's basically all you see how many paths, how many routes like this. For example, think like the edge 1, 2. You say how many edges might need to use this edge 1, 2. Well, edge E might need to use edge 1, 2. And maybe there are many like this. So I see how much capacity I should be reserving for that edge. Might want to use this edge. And I only have capacity of this F. So I see how much more capacity I need to the edge for this edge. It's kind of like it should be reserved or it's overloaded. That's the load of the edge. And again, I'm doing the same trick. Instead of taking one tree, of course, for every one tree, it's going to be a single tree is going to be very bad. So I take a distribution over trees and I see what happens on average. And then I take the worst edge on average. So hopefully, if they have a distribution over trees, then it's not going to be so bad. For a single tree, of course, it's going to be bad. Distribution over trees, then I hope that for every edge, the load is going to be small. The expected load is going to be small. Okay.
What
Yeah.
is this difference? The difference between the two notions? It seems similar to the distance map.
It's deliberately written this way so it will look similar, but I think you divide the other way around.
What?
You divide the other way around.
I see.
The roles of E and F are kind of like
Okay.
interchanged. This is like how many edges E use this edge F, while in the other edge you say if this edge E I have to count, add up all these things over there. And the transfer theorem says that if you can get one with factor rho, maybe rho is log n or something, or log k, you can get also the other one within the same factor. Okay, so I was initially hoping to actually go into this description of how things work here, but the problem is that it gets very messy technically, although it's not that long, but there are a lot of letters. I have to go through the letters and verify what everything means. And therefore, I decided to not go into this. So I leave it at this kind of like higher level. There's just this duality between these two notions, and maybe less than 5 lines of math manipulation tells you how to go from one to the other. Okay, so once you formulate it in this way.
Is this a minimax?
Yeah, I think, yeah. No, I think you don't even apply the minimax. Just like you look at the same matrix and you look at kind of, as Mano asked, like the transpose of the matrix. So you just rework the formulations. There's also a connection how to use this to do the tree mapping that I said, which is like another few lines of calculation, because this is very specialized definition. And you have to see how this definition relates to the definition we actually care about. And they're very closely related, but it's not the same. Okay, so here is the question how to choose. And I'm going to tell you a little bit about it, but not do the actual math. So how do you choose this family M? As I said, maybe it's like a family of trees, tree routes. So one suggestion is to use 0 extensions. So, and I think this was actually suggested by Moitra in his first paper. So what is the 0 extension for us? It's going to be similar to what you know, but maybe a little bit different. So a 0 extension of a graph G, and now I'm thinking about like the edge, sorry, the distance context. So every edge has a length. So what is, we have a graph G and length L. And the terminal set K. So now I want to get back to the terminal set K. So what is 0 extension? We have a retraction. So it's a map that maps every vertex to a terminal. And in addition, I want a graph on the terminals. And I want this graph on the terminals. So this, I'm going to call it H. So it's a graph on the terminals. We have also lengths on this new graph. So it's like new distances. And I have the property that whenever I have an edge in this smaller graph H, it agrees with the distance in G. But it's only on terminal to terminal distances. Okay, so here is one, so here is one, let's illustrate. Suppose we have this graph, and only 1, 2, 3, and n are the terminals. I forgot to put the yellow thing here, okay? So 1, 2, 3, and n are the terminals. So I want to somehow contract it into a graph of size 4 on 4 vertices. Maybe I do it using these circles. All right, so this is going to be my new vertex. Or maybe I want to do it in a star-like fashion like this. I'm connected, so I have this new vertex 1, 2, 3, and n, and I can connect them by any set of edges I want. Okay, so but if there's like the length here was 20 and here 10, then the edge from 1 to n is going to be the length is going to be 30, because the length here has to agree with the shortest path between these two terminals, not necessarily with this vertex. Okay, the circles represent the retraction. Right, so this vertex is mapped to this terminal. Yeah, I mean, is the definition clear? This is like the retraction. So basically, I have the circles represent, so the terminals are 1, 2, 3, and n. So this vertex is mapped to this terminal is mapped to itself. These two vertices are mapped to this terminal. Now the graph that I build on these terminals could be anything. In particular, what I wanted, as I said before, is a tree, because tree is very useful. So I want to have this tree, and then I require that the distance is going to be between terminals is going to be exactly what it was over there. Right? And the distance is going to be dominating this distance. This is in H are going to be greater or equal. This is in G because of this definition. Why? Because if look at the edge between 1 and n, there's an edge here, and we said it's just the shortest path here. That's fine. If there's no edge between, say, 3 and n here, then the shortest path here is actually you have to go to 1 and then go to 3, which means like you go from n in a shortest path to 1 and then in the shortest path to 3. And that might be a non-shortest path, but it's going to be at least as large. It does correspond to some path from n to 3. Unfortunately, it has to go through another terminal, so it's longer. Okay, but if you do it this way, you always get a new graph where the distances are dominating the original distances. This for the terminals. We're talking about the terminals. Okay, and then we can think about once we have this graph, we can think about the stretch of so again, probabilistic mean, instead of taking one, we take a distribution. 1 0 extension like this, we take a distribution, and the stretch is, or expected stretch, we say it's at most, it's alpha, it's the minimum alpha for which the expected distance is most alpha what the original distance. Okay, but here we actually measure it for all pairs of vertices, not only for terminals. The guarantee above is only for terminals, the dominating, and here we require this for every pair of vertices, in particular for the terminals. Okay, so from one side, this is only increase, but in expectation, they do not increase by more than alpha. Okay, so we have these 0 extensions. Now I'm going to have 2 examples for the 0 extensions. Okay, like useful families of 0 extensions. So the first example is when the graph H is a tree, which is what I just showed you. Okay, so that's why I showed it. So it's the same picture. Okay, but now kind of like I require H to be a tree. I have a lot of freedom in how to choose this, how to construct the H, which means how to put the edges, where to put edges. I put here just a random, some star, because it's a tree. So if you do it in this way, and you want to plug in the relevant literature on embeddings, turns out that you can use it's a kind of a corollary. It's not phrased in this way, but you can derive from a paper by Gupta, Nagarajan, and Ravi the following statement. There is an algorithm, it's even efficient, that for every in every graph G with K terminals and so on, you can produce a 3-0 extension. So it's a 0 extension like this, which is also gives you H is a 3, where the stretch is only log K. Okay, the point is that it's log K instead of log N. And the idea is basically use a variant of the embedding into trees that we know by Faccharoen, Folrau, and Talwar. Here are kind of like the major differences. We allow distances, they allow distances between non-terminals to contract. There is no requirement that terminals, the distance is dominating for non-terminals. Okay, so we actually allow them to contract, and then we can actually get better. We can get log K instead of log N. So it means that you construct a tree that maybe many non-terminals are mapped to the same vertex. So distance is in the tree is 0. That's fine. Then what happens? I want a tree on the terminals, right? Like this graph H, a tree on the terminals. So I want to get rid of all the vertices that are unnecessary there. So there are 2 types of vertices there that I might want to get rid of. One is that vertices that represent a non-terminal. So I can just move them to the nearest terminal and get rid of that. So I can move that non-terminal to somebody else. Because I have a retraction, it's not a one-to-one mapping, it's just going to be a retraction. And then I get rid of these extra vertices. And also there could be like spurious vertices, internal vertices in the tree that do not correspond to any vertex in the original graph. And this we can get rid of by this result of Gupta by losing a factor of 8. Steiner vertices in the tree, right? If there's like an internal junction in the tree which corresponds to no vertex in the graph. This way I eventually get a tree which is only on the K terminals. Okay, these are the ideas. Other than that, it's similar to this FRT result. Maybe there one other difference is that I didn't say that you do this FRT argument where you cut balls around certain vertices, but you only grow these regions from terminals. That's why you get log K instead of log N. You only grow these regions from the terminals, from the K terminals. Okay, and then if you use, so that's why I said, well, I'm not going to give you the details. If you use this result, this corollary, and the transfer theorem, where the family of mappings is basically all things that correspond to 3-0 extensions. Okay, so I'm not allowing you any tree, just those that come from these 3-0 extensions. And then we know that distance mapping exists with stretch order log K, that's this corollary. That tells us that there exist tree-based sparsifiers. Well, you have to see what the definition really means, but it does give you these tree-based sparsifiers with quality order log K, which is the first or second result that I mentioned in the beginning. Okay, so because of all these definitions, it's a bit tricky to work with the exact definition on the slide and get all the details. The second example is where I don't have a good name, so I'm going to call it induced zero extension. So where do you get the graph H? We want the graph H from somewhere. The edges, which are the edges? Right? The lengths are kind of like determined for us. Whenever there is an edge, we can choose the edges any way we want. So we're going to choose it by using the graph G. So I call it induced by G. So and I use the notation H sub F. So what is this H sub F? So now let's suppose this is like by picture. This is the retraction that we have. Now you see, whenever there's an edge between a blue blob and a blue blob, I put the same edge between the corresponding vertices. So on the top you can see there's an edge of length 20 between the blob corresponding to 1 and to n. So I'm going to put an edge between 1 and n. Okay, the length is not important here, just the location of edges. So basically it's like I contract this blue blob into one vertex and so on, and then I get a graph, maybe with parallel edges, so I ignore the parallel edges. But this gives me the structure of H. The structure of H is just determined by the structure of G. Okay, so I call it's induced from G. From G and from the zero extension, right? How do you, what's the retraction? And then if we use the following result known for zero extension by Faccharon, Harensold, Rao, and Talwar, there exists a zero extension with stretch alpha, which is log k over log k. Okay, and we use this structure H sub F. Then using the transfer theorem, we get a sparsifier with this quality. Okay, so once you go into this high-level scheme of using the transfer theorem, it depends on which zero extension you use. It tells you not only the quality, which is coming from the stretch, the distortion, it also tells you what is the structure. So here I got just a sparsifier. I cannot say much about this sparsifier. Before I got sparsifier, which was combination of trees, or convex combination of trees. Okay, here I don't have this structure, that's why I get a little bit better quality. What happens if the graph is planar? Okay, this was for general graphs. If the graph is planar, we can use similarly the theorem of Kalinescu-Karlov-Rabani, that there is an algorithm producing a zero extension with alpha equal a constant, with constant stretch, expected stretch. Again, we use the transfer theorem, we get a sparsifier with quality a constant, and we can make everything algorithmic. Okay, now here comes, I think, a question which is very interesting, is that if you do this, would you get a sparsifier which is planar? We would like to be a planar, right? We start with a planar graph G, we do this transformation, everything, we get a sparsifier H, and oh my God, it could be much more complicated than G. The idea that to work with this is to make sure that this H sub F that we construct is actually a minor of G. If it's a minor of G, we'll know it's planar as well. Okay, and in general, it's not true. Or in using what I just showed you so far, it's not going to be true. But that's what we want to do. So what is the problem? Is the problem that this, if you look here, the way you construct H sub F from G does not preserve planarity. In this picture it does, but in general it doesn't. Why? Because we just contract these blue blobs. And if this blue blob is a connected subgraph, then H is going to be a minor of G. But if this blue blob is not connected, then it might be not a minor. That's the only difference in what we're going to do. So what we're going to do is just make sure that the zero extension is connected. Okay, so we call an extension a zero extension connected if exactly this f minus 1 of x is connected in G. Okay, so here is by example, this is connected, this is not connected because the blob corresponding to 2 here, you have 2 vertices that are not connected in G. You have to go out of the blob to connect them. Okay? If all the zero extensions that we use, if they were all connected, then the graphs that we will be using are all going to be minors of the original one, and therefore planarity will be preserved. And we indeed give algorithms. The first algorithms that design or produce connected zero extensions. Okay, so for planar graphs, we can do this and still achieve stretch, which is constant. If you know what's the beta decomposable, it's like a tool in these embeddings, then we can get something with slightly extra log beta factor. So this, for example, this is actually the actual formulation how we get this constant. And we actually do it also for general metrics with stretch log k. So for general metrics, it means I don't assume it's planar, but I know that this h sub f is going to be a minor of g. Whatever g you give me, I'm always going to be using only minors. I'm not going to use like a completely crazy graph h. In particular, if you use, say, the first one, you apply this transfer theorem, you get a planar-based sparsifier, okay, which means like a distribution over planar graphs such that the capacity doesn't go up in expectation, or the capacity of any cut does not go up too much in expectation. Now, going back to this, so I won't talk about these cuts. Now we're going to stay with these distances, okay, like this zero extension and stretch. So what does it really mean in this connected zero extension? One way to look at it, and it's like the implication to embeddings, is that we can get rid of the non-terminals. We start from a graph of size n, and we only cared about the distances between terminals, and somehow I managed to throw away all the non-terminals and stay with a planar graph. Okay, and preserve all the distances within expectation at least. So here is like a theorem that a simpler version or something. I mean, that was proved by Gupta. That's the one I mentioned before. For every 3t and the subset of the vertices k, which we call terminals, there is a tree just on the k vertices that represents all the distances up to a factor of 8. All right. So if you have this 3t, I just copy it. But let's suppose now 1 is not a terminal. So you want just a tree on 2, 3 up to n. Okay, so we have to kind of like discard this Steiner point. We can construct the tree T prime where 2 is the center of a star and we have 3, 4 up to n. And distances are now 2 on every edge instead of 1. And therefore this is increased in general because this is between 3 and 4 is now 4 and before it was only 2. Okay, so in the worst case, this is like distortion 2. And he does it in general with distortion 8 for any tree. What we do in what I said basically in the previous slide, essentially, for every planar graph G and terminal set K, there is a probabilistic or distribution over planar graphs only on these Ks that represent all the distances faithfully. Faithfully means expected stretch constant.
For Gupta, there is no distribution. It's one tree.
Yeah, in Gupta result is what 1 tree.
And do you need, so distribution here is essential?
I don't know. That's a good question. I mean, I think it's believed to be, not believed, but people, let's say, are trying to prove it. Okay, I believe is a bit too strong for this.
It's some kind of beauty.
Yeah. No, I mean, that's one of the problems I mentioned later. Okay, and it turns out that the result that mentioned here that I just stated was used also in certain embedding results by Lee and Sideropoulos. So it's like simplifies their proofs. So I could explain a little bit how to do this because I think this is kind of like one of the nice features. I'm not sure. It's probably not going to be very useful for this audience. How to do it? It's too broad audience. Okay, so let me skip this. This is like how to use beta decomposition to get this connected zero extension. So let me jump to the open problem. So one problem is exactly what you asked, Steiner point removal, which is like you have this just distances. You have a graph with terminals, and the non-terminals are usually called Steiner points. You want to get rid of all the Steiner points and somehow maintain all the distances correctly. But of course, I could just use a complete graph on the k vertices. So to prevent you from doing that, I'm going to require that the graph that you construct is, if G was planar, the new one has to be planar. A version of it would be if whatever the graph you started with, I want H, the smaller graph, to be a minor of the original one. That's kind of a bit stronger because, of course, that implies planar, G being planar, H is planar. So here is like specific version, given a planar graph G and terminals K, build a single planar graph only on K that represents all the distances faithfully. So faithfully, you'd like it to be constant factor. So apart from trees, apparently it's possible also for outer planar graphs. There's like a draft that I think it wasn't published, but it's somewhere on the web you can find by Basu and Gupta for outer planar. It's a bit complicated, so I don't know if anyone looked at it to verify it. And more generally, you can ask, as I said, just use minor of G. Right? And therefore, if G is planar, then your new graph is going to be planar. But just don't use the fact that G is planar. For example, if you use a decomposition or some results like Plotkin, Klein and Rao, where you know the graph G is planar, now I don't allow you to do this because you don't know that G is planar. Another problem is, the name we use is something like S-sparse extension, so zero extension. So it's sparse, but not zero. So given a planar graph G and terminal is K, maybe instead of like restricting building something just on K, I allow you to keep a few more vertices. Say a set S, which contains the K terminals, and maybe another K or K squared more vertices in the original graph of your choice, and then build a zero extension into this S. So you have more freedom. Let's say what I had in mind is that I have to solve a problem like a flow or cut problem on a graph of size n, and I know I only care about K terminals because these are the vertices that my company owns or something. Now, in terms of space, it'd be great to reduce the problem to a graph of size K. The graph was of size 2K, maybe it's okay. K squared, maybe it's okay. It's still much smaller than n. So you can choose any like superset of the terminals, and you want it to be maybe polynomial in K. And do the same thing, but now you want it to be constant. Okay, this is I don't know how to do it. If you try to look at the lower bounds, where you know that zero extension requires omega of square root log K, this is results from CKR. In those contexts, like the relation between n and k, they're very small. Like n is something like k log k. So you cannot use those lower bounds to say that poly k are not enough, because in those lower bounds, the entire graph is contained in poly k. So you cannot use it to kind of like say that you need more than constant stretch. Similar question or different question is whether you want a single planar sparsifier graph instead of now for the cuts, not for the distances. And kind of like a more general note is that this duality between distances and capacities or cuts, instead of having it on the level of distribution over cuts, can you get it for a single graph? Like somehow we had to go to a distribution over graphs, and that gives you a weaker result, obviously, because distribution over planars.
This poly k, if you take this example with about k.
You mean from CKR? From CKR?
So the n is very close to k.
N there is very close to k, it's O tilde of k. So definitely if I allow you k squared, I can easily solve that problem because I just use the same. I do nothing.
So poly k for planar graphs is trivial.
Sorry, I think this was supposed to be for general graphs, for the S-sparse. Yeah, so good point. Thanks. Yeah, for general graphs. Yeah, so this question is basically, can you do it in a single graph instead of using probabilistic mappings or probabilistic distribution over trees, distribution over planar graphs? Somehow I want one planar graph to preserve. So what is duality? Maybe instead of just one planar graph, somehow you can take combination but make sure it's still planar. I don't know. But I think generally when there's this duality between distance and capacities, it tells you that you're right on the money. And then whatever I'm discussed about distances in the first few two bullets, you can ask similarly about cuts. Can you, if you have a graph with n vertices and k terminals, I only care about the cuts between the k terminals. Can you get one graph and like remove all the non-terminals and preserve all the cuts? Maybe if you allow a few more pseudo terminals, then maybe it's okay. You can do much better if I allow you another k squared or something, versus non-terminals to stay in the graph. Something like this. It's sort of a dimension reduction or some sort of like, not dimension, yeah, sort of a dimension reduction question when you want to go from n to something like k. And finally, I'm not sure exactly how to do it, but there might be some analogous questions for Euclidean, let's say two-dimensional Euclidean metrics, because like a planar graph in the plane, and it's like kind of like a connected region because of the minors. It reminds me something like a Euclidean metrics, but you have to formulate what exactly is the analogy with minor, and then maybe you can do better just because the Euclidean distances are much more well structured than general planar graphs. Thank you.
Are there more questions? I have a question. So do these results help in kind of improving the running time of the algorithm? So just to give a parallel with for edge sparsifiers, right? It helps to reduce the size of the graph, and then you run your algorithm on the sparsified graph. So does Vertex sparsifiers help with this?
It's a good question. At the moment, it doesn't. So at the moment, like building this sparsifier is like a somewhat heavy operation. I think the bottleneck, at least in today's technology, is something like this. To build a sparsifier, you need like depends on which context. So let's say a distribution over trees. Now the distribution has to be large, like of size omega n, the number of vertices. And there's no quick way to generate the right one that you need, or not going through all of them, and each one takes, say, at least linear time. So altogether it's like at least n squared time, at least. Maybe there would be a way to get something like indirectly get the right tree faster. And then it could lead to something like you pay maybe n, like something like order of n to just generate one tree. And then solving the problem on a tree with only k terminals, you can probably do fast. Right? But this reduction, so it's expensive, but it's not inconceivable that it could be done faster than what we know today.
In some sense, unlike for edge sparsifiers, vertex sparsifiers help only for approximation for runtime.
Well, that's a different issue. Here you lose, say, log k or log n in the quality of the cuts or the flows, while in these edge sparsifiers, you only lose 1 plus minus epsilon, right? So let's say you don't lose anything, right? And here you immediately lose a factor of log k. So at least at the moment, maybe for example, one of the questions here is like, if you allow you to use another k or k squared vertices, maybe you can do better. Maybe you do like k divided by epsilon squared. Maybe you do 1 plus minus epsilon, right? And then you could do this, something like this.
Great. Let's thank the speaker again.
Thank you.